The question states the beam is subjected to distributed loading. Determine the length B of the uniform load and its position A on the beam such that the resultant force and the couple moment acting on the beam is 0. So basically what this part of the question is saying is calculate these values such that the system is in equilibrium. So let's write that down. Summation of forces is 0, and the summation of moments is also 0. Now, before we start solving this problem, let's go over what a distributed load does. Now, let's say we have this wall here with a beam attached to it, and it has a uniform distributed load shown in green. Distributed loads are different from uniform loads in the sense that there are infinitesimal loads being applied throughout the distance, basically. It is often helpful to convert these distributed loads into uniform loads. So the same setup can be represented like this. We have that same beam, and we can utilize our knowledge to convert this distributed load into a point load. And the magnitude of this point load is simply the area of this distributed load. So that would be this base that I highlighted in red. So let's call that actually just base times, it would be the height. The height. So this simply means base times height, which is, in this case, the area of a rectangle. Now, the area equation is going to be different for each case. For instance, we have a case here where it is a rectangle. It is a triangle. The way you deal with triangles for finding area is obviously different. So let's solve this problem in order to demonstrate that. Starting off, let's solve for the total summation of forces. We can see that there are no forces acting on the y direction because all the loads are vertical. So we want to note that down by saying the total summation of forces in the x direction is 0. Now, let's do the y direction. When we draw a quick diagram where this is our wall and this is the beam, we will have 2 point loads once we simplify the system. One here and one here. So let's call this F1 and let's call this F2. Again, these are actually distributed loads like this. However, we can simplify them, and that's what we're doing. So distributed load. This will clutter the diagram. So since we already have the diagram with the distributed loads on the right, I will just be showing the point loads here, the simplified point loads. All right, so for the summation of forces in the y direction, we have negative F1 pointing downwards, so that's why it's negative. And we have plus F2, and the summation of these is 0. Now, let's use what we just discussed with regard to finding the area to find equivalent values for F1 and F2. So for rectangular distributed loads, so uniform distributed loads, F1 in this case would be equivalent to the base times height. So for uniform loads, all we do is multiply the base by the height. And think of the height that I'm highlighting here in yellow as like pressure. So you would think like, oh, for 1 foot, so in this case we have 40 pounds per foot, you could think of this as for each foot, I'm adding 40 pounds. So if I go 1 foot in this direction, I just added 40 pounds. Another foot, I added 80, 120, 160, so on and so forth. So now returning to our solution, we can do base times height to convert F1 into a point load. So we're getting a force magnitude right now. So since the force is pointing downwards, we have this negative sign, and that's going to be negative base, which is given to us by the variable b, times height, which is 40 pounds per foot, plus 1/2 times base times height, which is 60. So the reason why this is happening, obviously, is the area for a triangle is 1/2 base times height. So let's do some operations on this. So we would get b times 40 is 1/2 6 times 60, and simplify, this is 3. And then b equals 3 times 6 over 4, which equals 4.5 feet. So we already did one part of the question, so I'm going to box this answer here. And let's do the other part of the question, where we determine the magnitude of A. So in order to do that, we need to understand where these point loads act. So we're talking about the distance here and also the distance here. So for rectangular loads and triangular loads, when we simplify those distributed loads, where the equivalent point loads act is different. So the way we calculate this guy is different from how we calculate this guy. Let's demonstrate. If I have a distributed load that is like this, and it's acting on a surface, I will show the equivalent point load with this red arrow. In this case, this red arrow will be equivalent distances from the edges. So let's say this is 2 feet, then this also has to be 2 feet. So basically, if this whole distance is x, the magnitude of this smaller distance that is equivalent on each side will be x over 2. And this is also x over 2. Now, for a triangular load, so let's show it like this. If we say that the equivalent point load can be shown by this huge red arrow, then the point load that is equivalent to this triangular load will not be in the middle. So let me show that as well. If we have a total distance of b, or let's call it x again, the distance from the equivalent point load to this side, which is the side of termination of the triangle, this will be 2x over 3, and the distance to the side that like the triangle gets bigger on will be x over 3. The reason why this is happening can be proven with calculus, but I will not be doing that in this recitation. So now that we've covered how to sort of think about equivalent point loads and their locations on the beam, we can continue solving the problem. So I will be using this previous diagram, and let me change the color of each of those distances. So the bottom one is blue, and the top one will be green. So let's give these two guys some variables. So this will be, let's call this C, and let's call this other one D. So we can find D right away because the values given to us are numbers here. For D, it will be 10 plus 6 times 1/3. And that 1/3 is happening because if this is our point load, the distance here is 6 times 2 over 3, whereas the distance here is 6 over 3. I exaggerated a bit, it's not to scale, but you get the point. So this is equivalent to 10 plus 2, which is 12 feet. So we already have distance D. Now let's calculate distance C. We have an unknown here, which is A. Although we have that unknown, we can solve it fairly easily. So we have distance A, which is this distance, plus, if this is our point load, we have this distance, right? And that will be B over 2, and we calculated B to be 4.5. So we would do 4.5 over 2, which is our value for C. So let me set that equal to C. Perfect. So now let's use the summation of moments to compute the value of A. We already have B. All we have to do is calculate A. So our total summation of moments is 0. And let's calculate this about this point that I just marked in yellow. And let's call that point O. So this will be point O. So the moment about point O is 0. Now let's calculate that. We have two forces applying. We have this force and we have this force. Let's inspect their moment contributions. But before we do that, let's also, something I forgot to do, is to determine our positive moment axis. So if we have a counterclockwise moment, then it is positive. So let's see, what kind of moment is F1 causing? It is causing a clockwise moment. So it will be negative F1 times C. And then we have an F2, and that is causing a counterclockwise moment. So this will be plus F2 times D. Equivalently, we can say that this is, let's see, what is the magnitude for F1? We calculated that to be B times 40, which is negative 4.5 times 40. So that's our F1, times C, which is A plus 4.5 over 2, plus F2, which is 1/2 6 times 60, and we have D, which we calculated to be 12 feet. We know that this is equal to 0, and when you solve this expression, this expression only has one unknown, which is A. When you solve this, you simply get A equals 9.75 feet. And that is our answer.